So I want to talk today about a few things. It's a case study in zero-cost abstractions, framed with this high-performance message dispatch algorithm and the interfaces and the way we went about doing things and why. So I hope to tell a good story here. It'll be interesting, and you'll learn some new things and just think about things a little bit differently. I'm Luke Valenty, principal engineer at Intel. I'm lucky enough to somehow be able to work with Michael Case and Ben Dean on power management firmware. Since moving over to C++ a few years ago, I've also advocated C++ at work along with Michael and Ben. I'm a dad. I have 2 kids. I'm a Star Trek fan. I'm not a Trekkie, but I enjoy the shows. So there's going to be a lot of code on the slides. I'm omitting const expr, no discard, no accept in most cases. Just assume I would put them exactly where you would put them. And then we'll all be happy. A portion of the presentation is adapted from Ben Dean's message handling with Boolean implication. I'll talk about the message handling part and a lot of Boolean math, but not the implication part. You'll have to watch Ben's talk for that. So when you see me looking at Ben, that's when we're talking about his slides. So before I go into the details of this case study, it helps to understand what environment I'm in and what in the world does that actually mean? What does it mean to develop power management? Firmware and what are the features and what is that exactly? So power management firmware, well, it coordinates power on and off events for components in our system, in our Intel system. And I almost just left it at that because it's, this is the big job. When you turn on your computer, you expect it to turn on. But beyond going in and out of, the active state versus being asleep versus completely powered off, we manage active power versus performance trade-offs. We report on energy usage, being at some of this core central part of the system. We're in a lot of these flows. We're aware of a lot of power usage, and it makes sense for us to do this. And then finally, we protect against overcurrent and overtemperature conditions, among other random features that we end up getting tasked with. Our firmware has to be robust. Nothing turns on without it. It's like the very first thing that needs to get exercised when we get our first silicon back. It needs to be performant. The faster we can respond to events, the better power management we can have, actually lower battery usage. Our hardware itself on the chip needs to be power efficient, and that constrains us. And really, really importantly, we need to be highly malleable, and we need to adapt to new product requirements and new products every single year. So this is kind of like a block diagram that we've released a while ago about Meteor Lake. And the cool thing about Meteor Lake is we have a few different die in the package, a few different dice, what you would think of it as a chip. We package them together. And that PMC, that's what we work on, and that's where we write our firmware and where it runs. And now there's a couple of them. And this is a new thing for us. It's different. On our previous project, we had 1 PMC. And we had a certain number of components that we talked to and power flows. But now we have 2. And that kind of blew our minds a little bit. And we have different interfaces. And we have to manage the power of those interfaces. We have our whole new neighbors on our chip that came down from the CPU. And we have a new component in there that we actually have to closely interface with. We have some new IPs. We have additional power flows. And so we have to be open to change. We have to decouple our components so we can pick and choose. Okay, we have these drivers for this component. We have this feature here. We need to pick and choose that from one project to the next. And we have to be malleable so we can actually do our job, so we can execute the amount of projects that we need, and so we can adapt to whatever the requirements are from architecture. We want to support them. We have to be power efficient. So this means we don't get big memories because we're on all the time. And we don't want to kill your battery. It also means we need a power efficient processor. So we have a tiny, tiny little baby core that you probably couldn't see on our die without a microscope. And we get slow clocks. So we have to eke out every bit of performance that we can to do our job. And of course, we have to manage our own power states and do that well. With that, though, we have to be fast. We need low latency. We have to respond quickly. We have to have high throughput. It's in quotes because, it's not a very powerful CPU. But we want to leverage things like zero and negative cost abstractions, things that C++ really excel in. And so math and science are our friends. And we can work on our implementations, and we can figure out what kind of algorithms do we need to use, what are some fundamental math concepts that we can take advantage of, et cetera.
Yeah. Could you give me a number for what the lowest latency required to, the lowest latency requirement you have to meet?
That's a funny question. I can't. But it has to be fast.
Yeah.
Yeah. Yeah.
We say a microsecond is an eon. You say it in cycles, maybe?
No. It has to be fast. A microsecond is a long time.
Okay.
And we're not running on a 2 gigahertz, 3 gigahertz, out of order processor. Yeah. So, there's this triangle of trade-offs, and we've given up on memory and processor speed, but we have constexpr, and we can tolerate compile time. And again, our two friends, science and math, they can help us do really cool things. We have to be robust. This silicon chips, as I understand them, are made with sand and a lot of money. And when you put those two together, you get products. And so people are very unhappy if the firmware does not work correctly. That's very, very expensive. So the earlier we can find bugs, the earlier we can make sure that our firmware is correct, the cheaper it is and the happier we all are. And this includes things like survivability, right? We can change firmware. So how does this influence our firmware design? Well, obviously no cost and negative cost mechanisms for composition and extension. So we want to be able to compose things. We don't want to write crummy code that depends on very specific details everywhere, and we get a rat's nest of things. We don't want to do things like, we have this if statement and we just call into all these other modules, right? That makes us very sad. We've experienced that. We know what that's like. We need stable, extensible, and declarative interfaces. And I should have actually emphasized declarative more than anything else. And we want to enable correct by construction techniques. So the more things that we can prove at compile time, the fewer things there are to fail at runtime. And so based on these constraints and based on past suffering, we've developed this pattern. And it started out as a pattern, but it's turned into a library, the compile time initialization and build library. Basically, it lets us do nice things like register callbacks. We can have a series of callbacks. We can register a callback that's dependent on another one, and we can have very complex dependency graphs, and it figures it out at compile time. And things get inlined and optimized. We're not going through virtual pointers, or we're not going through function pointers or anything like that. But there's a way that we need to have a nice way to make that happen. And so we can organize our code in components. We can have a top-level project component. We have our different components for maybe devices that have drivers for. We need to interface with them. We need to talk to them for features, for power management stuff. Foobar and Baz. That's what we do. The details aren't super important. But within our components, we have there's another delineation of services and features. A service in CIB is something that can be extended, right? We can receive a message, for example, and where do we send that message to? There's a whole bunch of other features that want to register some callback with a certain condition, right? So features can extend services. And this is the strength, this is the ability that CIB gives us. It lets us do that very efficiently. We take our top-level component, and it gets passed into the CIB nexus. And a nexus is a confluence of things. If you watch Tony's talk, don't think of it as complecting, because in this case, We're not complecting things. We're actually bringing things together so that we can modify the services at compile time. So we can extend the services at compile time. So our features know about the services in our source code, not the other way around. And out of that, we get instantiations. We get the realization of all of the different services that we may need to access and call into now that they're extended. So features, they're controlled by the customer. Most of the time, I don't come up with a feature that we need. Most of the time, we have architects. They're like, hey, we have this new thing. You need to do this weird thing for it so it works. Or we have this new standard that we want to use. Or we have this new disaggregation, right? Like in Meteor Lake, you have this IOE die, and you're going to be in the SOC die, and they need to work together. Constant change, right? That's the only thing we can expect is constant change. And that's what we get paid to do. We provide value to the customer. This is the business logic, right? And then there's the fun stuff that I like. It's the services. We control this. We define this. We create stable interfaces for ourselves. We provide, the services provide value to us, to the developers, so that we can implement our features. And our source code dependencies go like this. Features know about services. That's important. This is dependency inversion. There's some nice things from Solid. So what does a component actually look like? Well, it's a struct or a class. But to work with CIB, it has this compile time declaration, this const expr declaration. It's CIB config. And so this component is exposing a PCI-E handler, some PCI Express message handler, right? So it's advertising to CIB that this is a service that I own, other people can extend it, and I can extend it too. And so it has some message callbacks that it's also going to extend that service with. The service itself, well, this is like a service name. So it declares an extensible interface that conforms to a type of service. So this is a message service, right? Somehow messages get sent to it, and it will dispatch it to the appropriate callbacks that have asked for them. So it connects, the service name connects a generic interface with a specific implementation. So under that message service there. So we have our name, the type, and its configuration. So we're skipping ahead a little bit with this one. That's what the little star is for, because we're going to see this a couple times. This is what our message callback feature looks like, right? It's the smallest part of a feature that we can have. It has a name. It says what kind of message we want. It has a predicate that says these are the runtime values I'm expecting of this message that I can handle. And if it doesn't have that, then I don't really care about it. And it has a lambda or a callable to do some processing on it. That's how we hook into a message service. And we have our top component, and components can be composed of other components. It's kind of like they were made for composition. The nexus, again, is where we bring everything together. And so you just instantiate a nexus, you pass it your top level component. This right here, just having that, does all of the compile time initialization and building process. I actually have a bug in this code because this right here is 100% going to be uninitialized. So you need to call a init on Nexus so that you get a type erased interface into all of your services. Otherwise, you could only access the service from Nexus, which makes for some impossible circular dependency when you try to call into a service from a feature that's extending a different service. So anyways, we have this type erasure provided through the CIB service. This I didn't come up with this one day and make it work. I had a lot of really bad implementations, and I didn't realize what I was doing exactly. But I knew I needed to do it because that callback system with dependencies was critical to us being able to do composition, and it didn't physically fit. It didn't physically fit if we do it at runtime, both in terms of time as well as memory So we had a specific implementation to do that, and it kind of worked. And then it was generalized a little bit to support message handling. Then it was fully generalized, but all the configuration was imperative, and it's terrible. Features were type erased when they were added to services. So we lost a lot of information and we lost a lot of opportunities. And the fourth iteration is the CIB library that's open source up on GitHub now. And so I did a whole talk a couple years ago at Embo++. It was virtual, but I'm certain that people's eyes were glazing over as I was talking about it, because I went into a lot of detail about how it works and showing code. And I had a lot of fun. And I think a couple other people did too.
Great talk.
Oh, thank you. So check that out if you're interested. The talk is linked on the GitHub. So message dispatch. This is our case study. So what is it? It's simple. We have a message. We decode that message, and then we send it somewhere. We have some other components in our firmware that need to process that. Let's look at PCI Express. So PCI Express is a great interface. It's been around for a while. It's based off of PCI. Many buses in modern computers, the internal buses, need to talk over PCI Express. And so it makes a lot of sense that there's commonality. But it's just a struct. It's some D words with bit-packed fields, and those fields have meaning and they have location, and we need to access that and process that. And so we get something like a PCIe packet from some network, from some interface. It goes to our message handler, and then it gets dispatched out to some callbacks. This happens a lot, and we want to do this efficiently. We want to do it quickly. It's not only used for hardware, though. You could use this for some event bus or message queue architecture beyond hardware bus protocols. But yeah, I always talk about what things should be. And the first thing is always it should be correct. It should be robust. It should work. It should do the thing it's supposed to do. But there's other attributes. We want to enjoy using it. We want it to be easy to do the right thing and hard to do the wrong thing. So let's start going backwards first. This is not too far off from how some of our code has looked in the past. And everything is wrong with this. This is not C++. This is terrible in every way. And so we're going to talk about the different ways it's terrible. Not type safe, not maintainable, error prone. Why is it not maintainable? It's not maintainable because you have a service that's getting these messages, and that service knows about every single feature you ever have and maybe ever did have, and that you maybe are doing, if defines or if statements to disable. So it's really terrible and error prone. We're 100% going to mess that up. So how do we make this better? Well, there's a whole bunch of obvious things. Type safety, compile time programming, identify and lift up the fundamental concepts. So what we're trying to do, what we want to do, the end result is completely conflated with how to do it here. And this is, this should make all of us unhappy. So we want to use declarative style. We want to decouple things. And we want it to be fast. I want to be able to change my dispatch algorithm depending on, I don't know, maybe I just get really excited one day about something and I start focusing on it, and I want to make it better, and I don't want to break everything. I want to be able to do that independently, and I don't want to have to go through the code base and change every location that we use this. Yeah, it's not foreshadowing, don't worry. So, we can clean this up, and all I did here is I noticed that there's these two fields that combined together mean packet type. So I simplified it a little bit. It's not much. But you know what? Wouldn't it be nice to have a type to represent that in enum? That would be nice. So let's do that. So we have that now. And then, raw pointers are we do embedded firmware. We don't need raw pointers for almost anything. There's very few cases in which we use them. There should be very few cases in which we use them. I can say that accurately. And we can use a case statement. But the other terrible thing about this is, we're just getting a span, right? There's no type safety in the fields that we're processing. We have to have these functions get packet type, but that's also just taking a span. Is this the right one? Is this get packet type for PCIe, or is it get packet type for USB or something else? I don't know. I'm hoping it's right. It probably should be because it's getting, that packet type. I don't know if that's the right one either. Anyways, we want a proper data structure for our messages, right? We want something that describes once declaratively, these are the fields we have, right? These are the names of the fields. We have this compile time string, and we use compile time strings all over our firmware, but we don't have a single byte of string data in our binary. We have a logging system in CIB that kind of takes care of that for us, and that was a talk last year that I did. And so we have all these fields. Fields can have types. This is just an alias for unsigned 8-bit integer. In our message definition, this is just a definition, by the way. The fields are definition. The message is a definition. They're empty types that contain no data. They just describe. A message is just a collection of fields. So now, we can, this is not quite right. This should be no, this is fine. Let's use this version of the message. This is the header. So the header is just going to contain a type, right? It's containing that same type field, but I don't need to know the other details. I don't know what kind of type of message it is exactly. The different message types contain different fields potentially, right? And so this is the bare minimum that I need to dispatch. So now I can just get the type. This is a compile time string again. So it's no runtime cost to do that. Probably a compile time cost. And we go through and process this. So we solve a lot of problems though. It is more type safe, but notice we're still passing this message. This is a const view. It doesn't own the storage, but it allows us to view the underlying storage through the message interface. We're still passing that same message data, and it doesn't describe the other fields. It doesn't describe, oh, if this is a memory read, I should have an address, and I should have a couple other attributes and a tag. We don't have that still. So we're not type safe. Yeah, because our process functions are just getting this header. We still have to cast to the more specific type. So again, not really scalable and maintainable. Now, here's the next level, processing a memory read, for example. Maybe we have a hardware register interface that our firmware implements. So our host CPU, operating system's reading some stuff to the power management unit. Maybe it goes to hardware, maybe it goes to firmware. Maybe we have different firmware components that handle different pages in the address space. So again, the different features have their own different register sets, and now we've put them all together. This is definitely complecting. We put these all together into this one location that should be a generic thing, and now it's not generic at all. Okay, so we can have a whole bunch of services, we have features, and if we implement things like on the previous slide, now our services are dependent on all of our features, which is terrible, because the only certainty that we have is that our features will change all the time. There's no consistency. They will never be the same. There's always something new that needs to go in and change it. And so that's not how we want to depend on things. We don't want to have our core functionality affected by that. Instead, we want to use CIB, and we want our features to depend on the services, right? So we can remove a feature, and it's fine. We can add a new feature, and that's OK, too. I don't think any of this is revolutionary. But fixing this requires a bigger change. We can't just kind of refactor it piecemeal on the slides. So we need to move over to the message services and message callbacks within CIB. So we can kind of work through this a little bit, though, in a similar way. Not use the final API that we have, but let's kind of reason about why we want that API. And let's work through, what are the problems if we don't do it right. So here, we have our message callback. It takes in a type of message, and it's just a Lambda expression, right? So the conditions that we need are within the Lambda. This is functional. This will work just fine, right? There's nothing wrong with this from the functional perspective. But we like to debug things. When we get a message, I want to know, does that message match one of our callbacks? Not only do I want to know that, I want our Val engineers to know that, so that they don't have to ask me what's going on. They can look at the logs and they can find out. That's very helpful. Finally, it helps us to take the message definition and move it into a template parameter. Because there's the hacks and tricks we can do to deduce what the message type is from the Lambda, but that's not nice. It's not robust. It doesn't, it's not guaranteed to always work. So we put the message definition type into, we expose that to the library. We expose that on the interface. And this will be more apparent why that's useful in a little bit. And finally, we actually want the predicate to be a first-class citizen of our library's interface. This is really important for us because, well, there's a lot of fun things we can do that help us out if we do that. Finally, so that we can get type-safe, like really type-safe message handling, we want our message definitions to describe the runtime requirements for that to be a valid message of that type. So the fields that are present in a message can depend on some type field or some opcode field or some command field. And maybe there's a subcommand or sub-opcode. Maybe there are flags that change the way that it's formatted, 32-bit address versus 64-bit address field, right? If our message definitions themselves also contain, for this definition to be valid, for a message to be this type, the opcode has to be memoried 32, right? And then it's valid. Now, our library can make sure, if we're going to match this, we're going to make sure that this is correct, right? We're going to make sure that the page field of that message is 0. We're also going to make sure that all of this message definition's requirements are satisfied. So it's going to be a memoried 32.
Okay, so I think you might have answered by the time you got to me. I was like, why couldn't you just do that with the requirement field that you had your predicate field? You could validate all that.
Yeah.
It's more about doubling it down so you can do it statically at compile.
Well, this is going to be evaluated at compile time, right? Not at compile time. This is known at compile. We're advertising this to the library at compile time. I want to put it with the message definition because whoever created this message definition, they're looking at the spec. They know what it's supposed to be. They're checking their work. It was reviewed. It's good. It gets into our code base. And then I'm going to add a callback. I'm like, oh yeah, I know what a memoried 32 is. And I'll say, well, the command is memoried 32. And that's what I put in. Except maybe I forgot, this other bit has to be set to 1, right? I can't mess that up now because this definition contains the requirements. So anytime I want a message like that, I'm guaranteed to only get that message. And then it gets combined with these requirements. So that's why, because I don't trust myself, right? We make mistakes. We have our name, our message type, our predicate, and then we have our action. Yeah?
That predicate is a DSL, just in case people are wondering.
Yeah. So that's a domain-specific language. It's a very obtuse language called Boolean algebra, Boolean expressions.
Sort of like unit test frameworks do their thing, or something that looks like an expression.
Oh yeah, some unit test frameworks will look at the expressions or overload operators. It's kind of like that. But basically, we know the AST. So I'll go into more detail on that a little bit. So we have our fields. Again, so you see Ben's names up here. I'm going to go look at Ben a little bit more often now. These are taken from his slides. We talked about fields a little bit already. But there's a few more things that we want to make sure that we have set here. So one of the nice things is we can actually have multiple field locators. So we can have fields split across multiple locations. Here's our same PCI Express packet example, the same fields for our memory read. We have our tag, which we use to compose the message, and we can use that in our predicates, or we can use the name in our predicates. So if we use the name, it's a little bit nicer because across different packets, you might have a different location of a field, right? And so if you use this name, you can reuse the same predicate for different packet types, which is kind of nice. You can use the same get method for that. That's not fully realized for dispatch yet, but it is fully realized for like getting the fields. And then our locations we don't have it in this example, but we could have multiple locations. So a field can be split across multiple spots. And then the fields themselves, they're empty types, but they describe how to extract and insert a field into a range, right? Our messages then are just compositions of fields. But again, this is an empty type. It's just the definition. It's just describing what it is. So we have an owning instance. So this contains its own array that fits all of the fields. And then we also have the const view and the, is it a mutable view, Ben? For basically having a reference where we don't own the data, but we also don't want to copy it. And we do this versus just using pass by reference because we have a certain message type when we're decoding fields. We don't know what message type it is yet. Once we see, it satisfies the requirements for this message definition, then we can basically say, okay, here's a const view of this message with these new fields. And we know it's type safe. And our matchers are something that we're going to talk a lot more now. So matcher, it's basically just, it has a callable that you pass in a message and it returns true or false. That's it. So it's a predicate on a message. Simple matcher that we're using in all the examples here is we have some compile time value is equal to the value of a field from that message, right? We can use the relational thank you. And then we can basically have one matcher and just stamp it out for the different relations. But we can also think about matchers as Boolean values themselves. And when you do this, or when Ben does this, there's a lot of fun math that you can apply to do transforms and extract information that we want to get performance or other characteristics that we want. But yeah, the resulting matchers are expression templates. And so we can do and it's just a composition of the left-hand side and the right-hand side. And then we evaluate both sides and return the and of the result. And the same thing for or, and same thing for not. And then we overload the operators so that we can compose these in a nice way. So we can define fields and messages. We can describe how to match on messages. And we can, combine the matchers into arbitrary Boolean equations. So if we're using this and you're not using the full CIB pattern, it looks something like this. You can, define your message. You have your callbacks. You can create a handler. Don't look at this too hard because this is not 100% correct. And then ultimately, though, on the handler, there's a handle function. And that's when you pass in your message, and it'll dispatch it to the appropriate callbacks. So, not only can we have, all of these, requirements must be met, it's an arbitrary Boolean expression. So we can have ands and ors. We can do relational operators, etc. So again, this took several iterations for us to figure out. The first version had no type safety. It was basically you pass an array around, and then there's these field declarations that you can use on an array, and then they know how to extract and insert data. That was embarrassing and it's painful, and I'm still paying for that sin. The second version had built-in storage and type safety, but some weird quirks with the way the storage was managed. And then we have the current open source version, which has been iteratively improved thanks to a lot of critical feedback from Michael and a lot of work from Ben. I did some stuff too. I filed some issues on it, and then they did the work. Thank you. So we have this declarative API, which is really nice, but we also we need to process these messages quickly, and that's kind of, besides the ability to compose our firmware and add and remove features as they're added and removed by architects, we have hard requirements on how quickly we need to respond. So then, that gets me thinking, how can we do this faster? And I was thinking about databases. There's use indices to speed up queries. Maybe we can do something like that for message dispatch, right? Except we kind of need to turn it upside down. A database will use indices to accelerate matching one query against many rows, but we actually want to match one row, one message against many different queries to see which one it connects to. But yeah, we can do this, because if you think about a row has fields, data structure. A message has fields that are specific values, and simplistically, a query has requirements on fields of specific values, right? So there's that symmetry there, and we can take advantage of that. It's a really simple case, and you'll see this implemented manually in many cases. So you have like a message, or you have an instruction, or you have a command, and there's like an opcode for it, right? So what you can do is, you create a map or create an array, and each entry into that corresponds to a command or an opcode. And then to figure out how you want to process this, you get the opcode, index into the map, and then you call the callable or the function pointer that you get from there, and that goes and executes it. Or maybe it's a default handler because nothing was found. So this is relatively simple. This is not, people do this manual all the time. When you need to accelerate the lookup based on multiple fields, it gets a little bit more complicated. But as it turns out, it's not much worse. So this map here is mapping opcode to a list of 0 or more callbacks, right? These maps are doing the same. Opcode to 0 or more callbacks, destination ID of some type to 0 or more callbacks. But there's one additional thing we have to do. So we do the lookups on the maps, and then we take the intersection of the callbacks, right? If the callback was found in the list that matched the opcode and the list that matches the destination, then you know that callback matches both of those fields together, right? So it's a memory read, and it's 32-bit, for example, something like that. And then we iterate over that list of callbacks, and we process those messages. So we need very fast lookup for this, and we need a very fast intersection operation, and our data structures need to allow us to do that. So let's go through an example of what that looks like. So let's say we have a memory read coming in, and this is our list of callbacks on the left, and these are the requirements the callbacks have. So it matches memory reads. Okay, so we've got a few different callbacks that match that, plus some logging callback that's going to log every message we get. It's for page B, so let's see who matches that. Well, this guy does, and then the log message does, and then there's some source ID here. And so this is matching a whole bunch of things, and not that one, but that one. So what callbacks are we going to need to execute? Well, yeah, exactly. So memory read for page B, and then log message, right? So that's not too bad. We can reason about that with our brains. The data structures we need are these indexes, right? So this is kind of coming at it from a different angle. So we have our memory read, so we're gonna get all of the callbacks that match that. Page index, page B, so we're gonna get the callbacks there. Source ID, index lookup, it's the default value, so it's all of these, right? Untrusted. So we take these and then we calculate, okay, what's the intersection? What are the common ones in all of these? Okay, cool. And then we're just going to execute those. So, we should be able to do this very fast, and it should scale pretty well. There's a few different options for the intersection calculation. In the presentation, I've saved the results to the end, just how I saved myself doing the benchmarks until the last minute. So we have interesting results. So we need fast intersection calculation and fast index lookup. We know the keys at compile time, right? We know all of them at compile time. So we can optimize our lookup algorithm based on that data. But our predicate structure needs to be manipulated a bit because we need to figure out, like, okay, we have this arbitrary Boolean expression. Now I need to extract what specific values is it expecting on specific fields, right? I know how to do that, working through it, right? So we have some index fields, some non-index fields. Like, I can figure that out. So this one predicate matches two different possible alternates. Memory 32, page 0, and traffic class 1, TC1. Or memory 32 and page 1, right? We got two rows. So I would like a table, right? I'd like to take that arbitrary Boolean expression and convert it to some kind of table. I know how to process tables. I know how to work with them. You know, that's something I can wrap my brain around. Those three conditions must be met. I mean, I shouldn't have included the header for this because that's not part of it. But either this one needs to be met or this one needs to be met. And for each one of those rows, that and that and that needs to be met. So we can, you know, rearrange our expression to match this. And it's equivalent. It's doing the same thing. It just looks different. And I know programmatically, I can think, okay, I know how to turn that into a table. I know how to process that. And that's sum of products form, which is great because there's all kinds of material on Boolean expressions and simplifying them, and, you know, it's like hundreds of years. It's math. So that's great. All I need to know is that it can be done, right? It's possible. It exists. So what we need to do now, we need to take our callbacks, and there's a bunch of processing that we want to do with them on compile time. So let's run through these transforms and see how we can get this predicate and this callback kind of like visually transformed and think about, okay, what does our code need to do for this? So the first thing, we want to combine our message requirements with the predicate, right? Because the message had a whole bunch of requirements. We want to include that. Okay, that's memory 32, great. And then we want to convert to sum of products form. Like, this is really easy on slides, right? And I was like, oh, this couldn't be too hard. And then what we can actually do is a really simple transform. Each product term, we just make into its own callback, right? We just replicate it. That's easy. Like, I didn't have to do a whole lot to make that work. And we give it the same callback function. So our callback function was factored out. It's, you know, referenced by both of these. Okay. But if we're only indexing type and page, then we have this other little pesky guy for traffic class. We need to deal with that somehow. Well, that's not too bad either. In theory, we just pull it out and we put it into the callback function. So now we have this kind of intermediate callback function that's checking the unindexed fields. Okay, cool. So now we have these two callbacks. We're going to go through and we're going to update the type index and the page index, right? So now for memory 32, it could be callback 0 or 1. Page, key 0 goes to callback 0. Key 1 goes to callback 1. And then we do the same for all of the callbacks that we have at compile time. We fully fill out these indexes. I'm really excited about this. I thought this was awesome. I did a talk at MBO++ last year in person describing this algorithm. But I didn't have this part. And I asked Ben, and I file a very innocent little issue on the GitHub. Like, we need to be able to create sum of product expression for this lookup. Like, I can't expect people to put it in that form automatically, right? So here's a bunch more slides adapted from Ben. My brother would ask me, "Hey Luke, how are you doing?" And I'd say, I'm doing good. And my brother would tell me, "You're not doing good, Luke. You're doing well. Superman does good." And now if you ask me again, I'll say I'm doing good. So Augustus de Morgan and George Boole, We stand on their shoulders. I stand on Ben's shoulders and he stands on their shoulders. So let's come back to these Boolean operators. We're going to do some fun things with these. We have this, what looks like an AST, because this is our DSL. This is a domain-specific language. Luckily, it's a very well-known and well-understood domain, right? And that's really important. That's a wonderful thing. If your declarative style is based on, your DSL is based on something that has so much history, it's not likely to change. So sometimes we know things are going to be true, like we have an index field, for example. Like, okay, I want to remove the index fields, set them to true. Right? I'm going to assume my indexing is going to handle that. And if we do that, well, me thinking with my brain again, I know I can simplify that. And I know that always has to be A. So that's great, it's A, right? But we have to explain this. We have to code this up in our library so that our library knows how to reason about it. It knows how to simplify them, and it's something that it can basically do every time. So this is a great question. How does the library know how to simplify things like this, like these inequalities? And it's a great question that I'm not going to answer today. So I'll point you towards Ben's talk where he explains this, and it's really cool. So let's start with the easier things, though, that we can do. Not worry about the inequalities, but just the specific equalities. So we probably want something that's always true and something that's never true, right? This is going to help us. These are some fundamental concepts that we're going to need to describe to our library. True and false are taken, so it's never and always. So we want to be able to simplify this. The compiler can do that, right? The compiler can simplify these things, but the compiler doesn't know about our AND class and our OR class and our NOT classes, right? It doesn't know about our matchers. So we can't get the result out. So we're going to create a function to do simplify. I got real excited when I saw this, because that looks very easy. But by default, you don't do anything. And then you need to specialize it. You specialize it for AND. If either side of AND is never, it can never be true, right? It's a 0 and 0, 0 and 1. It's never true, right? So we return never. If one side is always, then we can simplify the other side to just we can simplify the whole AND to just what the other side is, right? So we do that for both sides. And if neither of them are always or never, then we have to do the full evaluation. We can't simplify it. And we kind of do a similar thing, but different for OR. If either one is always, then the whole thing simplifies to always. If one of them is never, then it just simplifies to the other one, right? Yeah?
In the last case, how come you don't just return the original matcher?
Because you simplify the sub-expressions.
Yes.
Oh,
Thank you. Yeah, so at the very top, we have to simplify the sub-expressions. So we actually, effectively, we go down to the node, the leaf nodes, we're simplifying them as much as possible, and then we're coming back up. So Ben goes into a lot more detail talking about using implication for this. And it's a fantastic talk that was published yesterday. I highly recommend everybody to check it out. So I'm going to have some gaps here. But now our library knows how to do this. And this is important, because after it does this, it needs to figure out how to convert into sum of products or disjunctive normal form. So it's like the tables that we saw, but some additional rules. So there's no OR terms inside any of the AND terms, right? It's a two-level tree, right? At the top, we have ORs. The ORs point to AND terms, nothing else below that, besides NOTs. So the first two expressions, these are sum of products, right? The last two are not. We can't have a not at the top, and we can't have a not of a full product term that has to be transformed. And at the bottom, we can't do things like A and B or C and D, right? That's not in the form. Like if you think about it like visually, you can't take that and transform it into a table directly. So there's two things that we need. Well, three. Distributive law, and then we need both of De Morgan's laws. Distributive law is kind of like, like you're multiplying X times, B plus C, right? We do the exact same distribution with Boolean algebra. I don't know if De Morgan's laws have the equivalent in arithmetic, but De Morgan's laws allow us to convert things between and or, right? And so the same way that we implemented simplification, we want to do that for sum of products. So we want to take our simplified expression, now convert it into sum of products form. You know, it appears that way when somebody's done all the work for you. Yeah. So if we have a not, we can't have a not at the top, right? So if the matcher inside the not is an and, then we use De Morgan's laws to convert that into the or of the two negated terms, right? But while we're doing that, we still want to recursively perform the sum of products transformation. If the underlying matcher is an or, then again, we want to do De Morgan's laws and we want to transform that into an and. Yeah, okay. I was going to ask Ben a question, but then I'm reading my own notes. It answers it. So we need to do this to get any ors out, right? We want to make sure that we don't have that. So we have to apply that again. If neither of those apply, if it's not an or an and inside, then it's going to just be a bare matcher, right? It's just going to be at the bottom of the node. So we just return that. We return the not. We don't actually apply any transform. That gets simplified out. Yeah, but that's yeah. So for or, imagine we're at the top level. Or is the sum, right? If we're at the top level and we're applying it, we don't actually have to do anything else, right? We don't need to do anything special. We just want to recursively apply it.
Is it just a two-level tree that we're trying to get down to, or for?
It's ultimately going to be just two levels. At the top, it's going to be or, and at the next level, it's going to be and then it's going to be the nodes, the individual.
Conceptually, yes. All of the templates, the or, t, and anti, they're only binary templates, right? So as a human, we can think of variadic or. It's actually implemented with binary.
Oh yeah.
But conceptually, yeah. It's the same.
Yeah, that's a slide that didn't make the cut. It's hard to do it variadically. Binary is easier to reason about. Ben has another talk.
So when I got from the root to the leaf, I just see a bunch of ors, then a bunch of ands, and then the leaf.
Yeah, but what you'll never get in sum of products, you'll never get ors underneath the ands, right? Okay. So Ben has another talk where he goes into much more detail on this portion and also pruning out conditions that, pruning out terms that we're not using, for example, because we're already handling that in the indexing. So there were two super important things that we need to do for this overall algorithm to be fast. There's more than two, but there's two that I'm thinking about and that I was thinking about. The first one is our indexes have to be fast. They have to be very, very fast. We need them to do our lookup quickly. The other one is we have to do a fast intersection, right? And then the other details are all the ones that I wasn't paying attention to, but we'll get there. So the cool thing about lookup algorithms and like hash maps and binary searches and these things is there's tons of material on it. There's a lot of research. There's papers. There's libraries. There's Wikipedia articles. There's YouTube videos. Like there's so many resources and other like implementations that people do. So there's a few things we have for like, you could do a linear search. Linear search is actually fantastic for small counts. It's great. Nothing will beat it for small sizes. Yeah. Binary search is okay. Hash lookup is fantastic. The library implementations aren't const expert in C++20, so can't use them. Also, like, When they are const expr, you build them in const expr, you can't get them out directly, into runtime, which is awkward. So we can't really use those. So let's not consider them. Again, linear search, great for small numbers, but maybe you do want to use find if, maybe you don't. Maybe the architecture that you're running on, like it's really fast to do conditional. Maybe you want to guarantee like a certain, like the worst case scenario, you want to guarantee that, but you don't care about the average. But yeah. Binary search is actually pretty slow if you don't need ordering. So I'm going to ignore that. We'll compare it, but I'm going to kind of ignore that. We want hash lookups, right? For large numbers of keys, like a generalized solution, we want a hash lookup. And so there's a library called Frozen. Frozen's pretty cool. It has this minimal perfect hashing. And minimal perfect hashing like really caught my eye. I was like, okay, I can do this at compile time, and it's going to optimize the hash function based on the keys. And it's going to be minimal. So it's going to be as small as it can be. And then it's going to be perfect, which is like, you can't get better than that. So I'm super excited about that. So here's some benchmarks. Std map is in blue. Std unordered map is in orange. Like, it's good. This is not good. It's linear, or sorry, it's not linear. It's like log n. But a binary search also has a data dependency between like, how you branch and, on a very small pipeline, like, a few, like 5-stage pipeline or less, that's not a big deal. But once you start getting more than that, you start introducing either branch mispredictions or, stalls in your pipeline, and that's not fun. And like std map is terrible for locality. Just don't use std map. Yeah. So I do embedded work, and we need to like have efficient storage as well as performance. And so these are our data sets: 1, 2, 3, 4, 5, 6, 7, 8, 9 entries, 10 to 90, 100 to 900. I also did 1,000 to 9,000. Turns out I didn't need to do that. We like, this is like we kind of live around here, right, for what we do. So we want this to be fast. Frozen map performance is not looking bad in terms of size. Actually, in terms of size, Frozen map is perfect. Like this is the ordered map. So it's just a sorted array of all the entries, right? And then it does a binary search on it. So we're going to use Frozen, right? Well, it wasn't quite good enough. I mean, I wanted more. I don't want to compromise. Like a good engineer doesn't compromise on anything, right? You have all your constraints and you satisfy everything without compromises. Well, unfortunately not. But then I saw one of Chris Druziak's libraries, MPH, perfect hash library. Like, of course, okay, I have to look at this, it's perfect. So I'm looking at the GitHub, and I see this example, and I look at the code, like this is the code gen. I'm like, what the heck is going on? Like, Frozen's code gen is like this, right? No, Frozen's code gen goes from the top of that to there at this font size. And it's like no branches, basically. So it's like a good indicator of how quickly it's going to be on an embedded system for like a small microcontroller. So I'm trying to understand what's going on here. I'm failing at understanding. I don't know what that instruction is. Does anybody know what that is? It's cool. Parallel bit extract. It's very cool. So I add that to my benchmarks. I'm like, oh my God, look at that. Like, what's going on here? My data was going further, but I was talking to Chris, and I'm like, and he's like, well, you shouldn't really use it for more. It's like, it's intended for smaller sizes because I don't have a size graph, but when you add in like the size, it's like kind of shoots straight up. It's a perfect hash function, which is awesome, but it's not a minimal hash function. A perfect hash function can also be, the identity function on a 4 GB array, right? It's perfect. You're not going to get any collisions. You're not ever going to hit cache either. But this is like, okay, I want that, right? I want that very badly. I don't have this instruction on my embedded processor. This is a very specialized instruction. It's too good. I can't pass that up. So,
Is his code have a literal PX, or is he writing code that becomes compiled to that?
yeah, so he writes code that's compiled to it, and it's called like underscore PEXT. So there's an intrinsic that he's using. Yeah, sorry. So let's zoom in a little bit. This latency is ridiculous. It's nothing can touch it really, and it's consistent all across. So this kind of blows my mind. Remember how I was saying there's only like 2 things that I need to look at for performance, and well, this distracted me. But it's worth it. It was worthwhile. So what this does is basically you give it some data, and then you give it a mask. So this is your source data. The mask is the control. And the mask basically says, for each one of these bits, I want to extract that. So that's cool. It's like a bitwise AND, right? No, because it takes those bits and then it packs them all. It's like really cool. And I'm like, how does this work as a hash function? Like, I didn't understand this because I had spent so much time. If you look at my talk from last year at MBL++, I spent so much time like figuring out, oh, you can just make a whole bunch of like fast but bad hash functions and then go through them, and hopefully one of them is going to be good enough and also fast enough. This is like an algorithm that picks the mask to use for your keys to find one that has no collisions. And it gets even cooler than that. So I'm looking at this and I'm so jealous and I want this. I'm trying to figure out how this works. Like, okay, so what you do is you do what I just said. You figure out what mask can I use where I iterate over all of the keys and they're still all unique. There's no collisions, right? That's like not bad at all, actually. I mean, I could understand it. So then you generate the table. You fill it. My algorithm is something's not found. You use the default value. It works well for indexing. Fill it with the default entry, and then you just go through like, oh, I'll just take the mask, do that, put that into the table. Your table needs to be big, 2 to the power of however many bits are needed, right? So if you need 6 bits for it to be unique, then you need a 64-bit entry table. That's not big. It gets big, yeah?
Maybe I'm jumping ahead, but when I see something that says, well, the table shouldn't be too big, I start thinking about a 2-level table.
Yeah, me too.
Okay.
Yeah. So I was thinking of all kinds of crazy things. Most of them were crazy. But I was on a mission. So how does the lookup work? You apply PXT to the key with your mask. You index directly in the table. You get the entry, and then you just check: is that the right one? Because it might not be, right? You can have aliasing. If it is, you return that. Else, you just return the default value. That's so simple. Like this is, just a handful of instructions, just like what we saw. Like Chris was not messing around. So I want this still. Ben?
You said you can have aliasing, so it's not perfect. That's an engineering choice.
No, you could have aliasing because you can't trust the data that you get. You could be getting a key for something that you don't have. It doesn't exist there, and then it might alias, right? Do you have a question? Okay. So how can I do a parallel bit extract?
I was going to ask, MPH has other policies. Did you test the performance of any of the ones besides PEXT?
I was really interested in just this one. Yeah. Chris has a bunch of benchmarks on his page though. And he made 2 releases since I started talking to him. So,
Open the package to light and find the algorithm for it?
no. I mean, that would have been cool. This is a algorithm, right? This is a way to do it. This is awful.
Just let this plus optimizer.
No, yeah. See, the thing is, it's not going to be good enough because, well, you'll see in a moment. What I could do is I could extract each bit and then I could just pack it, right? That's what this does. This is slow. Don't do this ever. I could also look for runs of bits and then pack them. That's a little bit better, right? Yeah?
Since you are controlling all the data in the way it's, do you need to use packs at all? Could you just pack all the bits in the lower part and just use the bits?
The architects define the bit encodings. And unfortunately, we're not the most important people to them, and there's legacy. And so, yeah, we don't, this is where we need to be malleable. We need to adapt to whatever we get because we're going to have to deal with it somehow. Okay, so this is, yeah, that's a terrible algorithm. So I start Googling around and I come up to Stack Overflow, and this looks like it's something from like a chess algorithm maybe, you know, packing bits into 64-bit editor. But like, okay, some interesting techniques using multiplication. And I was clicking on some of these like, oh, yeah, multiplication. It's a bunch of shifts and adds, right? So we can shift stuff around. I could align the bits the way I want them to be aligned, right? So 12 times 5, right? Let's just go over it. Multiplication, right? 12 times 5 is equal to 60. Well, 12 shifted over 0 because we have the 0-bit set. 12 shifted over by 2 because we have 0, 1, 2, this bit set. We add them together. Hey, that's 60, right? Generalized for 4 bits, we have 4 bits A, B, C, D on one side. On the other side, we're choosing which shifts we want to add in, right? We go through and we'll add the ones that are enabled. This is what I want, though. I want to be able to line up my bits. Okay, so if that's the case, I should be able to find, so first I want to mask out my interesting bits. These are the bits that I want to use. These bits are the ones that guarantee all the keys are unique if I process them. And then I want to figure out some magic number. So I get the interesting bits, they're not packed together, but if I multiply by this magic number, they're going to be all packed together. They're going to be shifted up a little bit, and I'll have to shift them back down. And then there's going to be a whole bunch of garbage carried up from, because I'm doing additions, right? And I'm not masking off at each shift. So there's a bunch of like other noise. So this is not going to be a perfect parallel bit extract, right? There's going to be overlap. There's going to be additions happening that I don't want. There's going to be carries getting propagated. It's not a real PEXT. It's a pseudo PEXT. So the compiler would never have like optimized this and be like, oh yeah, do a multiply. That's good enough, kind of. But it's good enough for hashing. It's fantastic for hashing. So here's an example. I want to extract this bit. This is going to be bit A. This is going to be bit D. I'm going to extract both of these from this value, right? Our magic number is 5. It just is. I'll explain this more. So what we need to do is multiply by 5. That's going to take this one. It's going to keep it here because bit 0 is set. It's going to shift this one over because bit 2 is set. Add them together, and look at this. We got these two guys right next to each other, right? That's promising. And then shift it over. Shifting is so easy. It's not a big deal. And then you mask it. There we go. So we have a pseudo PXT. This example was picked so that there's no conflict with the bits. Nothing's getting added together. It happens. It turns out it doesn't matter, right? I was going to be like, oh, do I need a more complicated algorithm to like do it in the most optimal way to minimize that? Nope, I don't. And I didn't, so thank goodness. That would have been a lot of time. So see, this algorithm is really easy. Basically, find each consecutive run of ones in the mask, right? And then calculate how far it needs to be shifted. So the highest number of ones, you keep them where they are. The next level of ones, you shift those over. The next level of ones, you shift those over. That's why it ends up higher than what they were before, right? And then you just don't worry about the other bits that are adding, right? It's okay. Hash functions in general are shifts, XORs, and multiplies, right? And they're just like, they literally, people like look for numbers that just kind of swizzle the bits around good for generic, data sets. So this is much better than that for specific known values. I was so happy when I saw this. The blue is the PEXT, it's Chris's algorithm. The green one is the pseudo PXT. It's a little bit slower, trust me. But this is 1,000 entries and it's maintaining that performance. So I'm really, really like stoked about that. This is the size. So this is why Chris is like, yeah, you shouldn't really use it for more than 60. It's because, you can't do anything else in an embedded microcontroller, but you can look up tables really fast, one table really fast. So it's perfect, but it's not perfect, It's perfect in that there's no collisions. You know what? Collisions aren't that bad. They're actually like really, really useful. Another thing we can do is we can add another level of indirection. Like we're having a whole bunch of empty space for our whole entries, right? But we only have 100 entries, let's say. Well, you can index into the final storage, right? So you can have a smaller lookup table as a smaller type. So let's add that. Yeah, it's less terrible, but it's still not good enough. So with one level of indirection, we're saving some storage. But what we can do now is it doesn't have to be perfect, right? So that indirect one is still perfect. It doesn't have to be perfect. If we get some collisions, it's okay. Because like, remember how I said linear search is actually like really quite fast for small numbers of elements? It's still fast, even if you're doing it as part of a hash algorithm. If you're like going up run through memory, right? Consecutive locations. So we're gonna figure out how we can update our mask search algorithm to allow for collisions. And we take so this is the perfect mask, right? Perfect. And okay, as long as we're configured for search length greater than 1, and also we want to stop eventually, right? I discovered that. So if we're down to like a 16 entry, intermediate table, that's great. Like that's fine. We don't need to go any more than that. What we do though is we find the bit that we can remove that results in the fewest number of collisions, right? Just one bit. So we go check all of them. Which one results in the fewest number of collisions? Okay, let's try that one out. And then we check the maximum, like the worst case number of collisions. What's the largest bucket that we're gonna have to deal with? If it's still less than our max search length, we're like, okay, we're gonna keep that, and then we're gonna go through again. We're gonna keep removing bits. We're gonna keep trying to remove bits that cause the least number of collisions. This is fantastic, it turns out. So just two items per bucket brings us down to here, right? This is better than the frozen unordered map. This is better than stood map and stood unordered map in terms of size. And then there's diminishing returns, but it just gets better and better. Yeah, so the best ones are all the pseudo PXT with a search of 2, 3, and 4. And then frozen map is perfect because it's just an array of the sorted elements and it's doing a binary search. Performance is also actually fantastic. So we have, I'm just gonna add all these guys in. Like they're all bunched up down here. They're all extremely fast. They're in like a whole different category than the other algorithms. So this is for 100 entries, and each entry is a 16-bit key, a 16-bit value. That's kind of a nice area, but I also have some benchmarks for 32-bit, which show similar results. 1,000 entries. We're not gonna have tables of 1,000 entries, but I would like to know that I could if I wanted to, if I had to for some reason. So like these are very reasonable values. This is a 66% efficiency in storage, right? Hashes are usually like this is reasonable storage efficiency for hash maps. So we're up at 66% for 1,000 entries, 83% for 100 entries. So that's pretty fantastic. And look at the speeds. Even with 1,000 entries, it's really not getting, like it's fast. It's still fast. So that's great. Yeah, math and science are awesome. Searching and researching and just making connections and trying out different things is a lot of fun. So let's put it all together. Remember, there's two things that you have to have for performance, right? Last year, I ran these benchmarks on a dev board that's representative of an embedded system. This is the dev board. It's not easily accessible. It's expensive. Why would you buy it, right? So it's not a great way to reproduce benchmarks. So I wanted people to be able to reproduce these benchmarks. This processor, I mean, it's pretty cool, but there's one little detail that's really subtle that you might not notice. I don't know, yeah. So hopefully that's obvious. Last year I ran benchmarks on the whole index algorithm, the whole dispatch algorithm, 150 callbacks, each one different fields, and I'm just going through a list of messages and I'm benchmarking it on the actual hardware. And I get this, and this is the dispatch speed for the index handler, right? It's less than 145 nanoseconds on a 400 megahertz in-order processor. That's fantastic. This is the naive approach, which just iterates over all the callbacks. There's like red flags here. The compiler is falling apart, right? It's doing great until like here, and it's like, well, I'm just gonna give up. I don't know what happened here, and then somehow it gets better when you add more. I don't know what's going on with this, but this was very bad. This was running on actual hardware though. So I was like, okay, I'll have to take a look at that. I really need to take a look at this again because this is multiple orders of magnitude faster. 1 year, changes have happened in the library. I'm running on a big core now. I'm running on like an x86 processor. I tried running on my laptop. My laptop never gives consistent results because there's like a whole bunch of stuff running in the background. It's my corporate laptop. So I'm running on a cloud machine, Google N2 instance running Cascade Lake. Very consistent. But this is, so I ran my benchmarks last night and then I ran them again this morning and I forgot to update this. So this bottom one here, this is the naive approach. This is the quote unquote naive approach where you're iterating over all 200, my code is iterating over all the callbacks and then evaluating the predicates. The compiler has got to be doing optimizations and combining things into like a binary decision tree or something, because this is much better than I expected. The index lookup is 20 nanoseconds. So it's faster. It's not like, it's 100 times faster. That's not what it is. The other thing here though, this naive lookup is still using the CIB library. So even though we're extending all of these things with features, at compile time, the handler knows all of these predicates, and the compiler can inline all of them, right? Because it's as if we're calling them all directly and getting inlined. So the compiler is able to do a lot of optimization here that I didn't expect, and this needs to be investigated. We had another way of storing the callbacks, the callback sets, so that we could do an efficient storage and then intersection. Way slower than expected. But we haven't spent time improving that yet. So, yeah, I was really disappointed with these results. It's actually quite good. It's twice as fast. And if you had a type erased system where you're registering things at runtime, you wouldn't get this kind of performance even in the naive implementation. And then also on top of that, like, compiler changes, some library changes. Now, this is an out-of-order processor, right? So maybe things like having an array of function pointers, right? And then having effectively a random index into it. And they're like, oh yeah, I want to execute the code at that function pointer. Probably not so easy for the CPU to optimize. It can't really speculate, right? It's going to speculate wrong every single time. Some lessons learned. So there's some things that we should be afraid of and things we shouldn't be afraid of. You shouldn't be afraid of change. You shouldn't be afraid of fixing things and improving things. You should be a little afraid of having the wrong interface. Like, you should have a healthy fear for making the wrong interface. So let's create good interfaces, depend on them, coax out the fundamental concepts. Like, what are the first principles? And then take those fundamentals and make that into a declarative interface. Just declarative, describes what you want. Then your implementation on the other side of that can be free to do many different things. And if you depend on such a stable concept as Boolean algebra, well, like, okay, it's been around for a couple hundred years at least. I don't know how many years. Do you know, Ben? Before I was born. Yeah, 1800s. So it's ancient.
Probably invented in India a few centuries earlier.
Yeah. Yeah, I mean, these are well understood, well researched things. And so if your fundamentals are that's a great sign. When do we optimize? Well, don't optimize the day before you're doing a presentation. That's not going to get you where you want to go. Don't do it the few weeks before, because you'll get distracted by something and not like, you need the measurements to know where you have to optimize, right? But the performance requirements, so the performance requirements should guide our design. So our overall design, like, I know I have to be fast, so let's make sure that I can become fast, right? And then optimize the implementation when you have proof that it's necessary. And you decouple the interfaces from the performance. So I'm upset it's not as fast because it would be so cool to say like, oh yeah, this is 100 times faster. It's amazing. Everybody should use this. But it's actually totally fine because we can always make it faster later, right? And we don't have to change our interface for that. So thank you, everyone.
Great talk. Thank you very much. So you mentioned that the hash function is not minimal. So you're basically sort of like in compile time heuristically looking for various hash functions until you find a good one that has not too many collisions and not too small table. So can you talk a little bit about like when does your search end, or do you like have a very long search when you compile for like release mode and small? Does it matter to
So
dial it down on debug fields?
test mode and release mode are the same for us. We always compile with O3. We just compile it the same way every time. There's fewer things to validate, right? It's like, oh, this test failed. Oh, but I was doing it in debug mode. Okay, is it going to reproduce when I do a release mode or vice versa, right? So that's kind of a pain. Basically, like, if you look at the graphs, a search length of 2 is really good. So that's the default for the indexes. So that's the criteria. So it keeps searching until it gets to a point where like I can't remove any bits without exceeding the maximum search length, right?
And will two compilations search like consistently in the same order and find the same match, or is there any way to get randomness into the compilation phase and it doesn't matter?
If the set of keys doesn't change, it's the same. It's a deterministic algorithm, yeah. But to find like that initial mask, if you start at the most significant bit, you'll get a different mask than if you start from the least significant bit. So I start from the most significant bit because a lot of times, like the lower bits, if you can remove all the upper bits, a lot of times you'll get a span of contiguous bits at the bottom. And then you don't need to do a multiply. Like the compiler is smart. It's like, oh, you're multiplying by 1, and then you're shifting by 0, right? That's just an and. Well, and then a mask. So 3 operations. So it just gets rid of the shift, gets rid of the multiply, and it just does the mask. Yeah. Yeah.
On that graph showing diminishing returns, so this is a graph measuring the size being used.
Yes.
So what is to make sure I understand correctly, the trade-off is time for the lookup due to the size of the search
Yeah.
that's required? Is that correct?
Yeah, exactly. So, well, yeah, but you know, it's not much of a trade-off, to be honest. So this is with 100 entries, with 1,000 entries. So a search length of 4, 2.06 nanoseconds. A search length of 2, 1.99 nanoseconds.
Have you found like a nice like optimal point where it balances those two parameters? Or does it depend on the use case of the
I think like a search length of 2 is pretty good. Like already just allowing 1 collision per key is quite good. It makes a huge difference. Like no collisions, you have a 10% utilization, 36 kilobytes. Allow for 1 collision, 12 kilobytes, right? 32%. Allow for 3, it gets better and better. So it's kind of like, it depends. For a certain data set that I have, like for a specific use case, or like, you know, search length of 2 is extremely good. Went from 4 kilobytes in size to like 400 bytes in size. And I'm like, yeah, I can live with that. And I hacked together a terrible lookup algorithm before, and this is replacing that. And so I'm very happy with it.
Is it guaranteed that all the service and features running on the same fields? Like they have exactly the same schema, I guess?
So for
Like what happens if a feature has, or a service has like more fields?
yeah.
Like you have the wrong hash map.
Yeah, so what could happen is, so right now, you have to specify, like for the index message service, you have to tell it, build an index on these fields. You have to do that correct, right? You have to put in the right fields. It's not going to do any checking. It can't. The other thing that could happen right now, and this could be changed, this could be fixed in the future, like you could have like a PCI Express handler for PCIe messages, but then you like add a USB callback. That's not going to work correctly at runtime, but there's not a mechanism to prevent that currently. But that can be added. Roy?
I don't. The cost of collisions is basically, I think, branches and branch predictions. Sometimes, I'm not sure if that's the case. And if you have like a deep pipeline processor and a bad predictor, or it's very hard to predict those things, then you might suffer.
So with this data, the way I ran the benchmark, these are always hits, right? But I actually iterate over the entire list. So each iteration through the micro benchmark, I'm selecting the next entry in the table, which could be anywhere in the actual hash map. So this should account for branch mispredictions.
Oh yeah, of course. But, yeah, so what I'm trying to say is that there are talks by, I think, Eduardo Madrid about this concept called SWAR, which I think is relevant or is applicable to embedded, where you sort of like look at like an entire collision list in one arithmetic operation and find the index within the like 2 or 3 or 4 short list of collisions. So maybe.
Yeah, I think that's something I need to look into. Chris's library has a SWAR algorithm as well. Yeah.
Yeah, so just to make sure that I'm on the same page, 1,000 entries means that you've got 1,000 callbacks that map to the same message structure that's coming in. Make callbacks on.
So for this one, this is just a lookup. So this isn't like the whole callbacks and everything. But at the very end, I have the benchmark for here. So this is 256 callbacks. Each callback has 3 requirements on 3 different fields. It has requirements on 3 different fields, right? So this is for the whole indexed algorithm. This is the benchmark for that, right? So we're getting like 40% faster.
So that's the total search space, and that it's not the number of things that have to be matched.
Yeah, so we're only matching on 3 fields here in this benchmark. Yeah.
And what's the typical number of matches that you have? Like you get a message coming in, and now I've got to make 2 or 3 or 10 or 20 callbacks.
It's like you could count them on 1 or 2 hands, like the number of callbacks that would match probably.
And when the matching occurs, is there anything in there that specifies the order in which, if you have multiple things matched to the same message, is there something that specifies the order in which they must be executed?
Not currently. It's something I've thought about. I'd rather not do that. It's nice to think about different things being independent, but sometimes there are dependencies. We haven't had a need to do that yet.
Thank you.
Yeah.
I had a question back at the expression simplification.
Okay.
At the very root, you said like, oh, there's a true here because it's a dynamic one, right?
Okay. I didn't. If I said dynamic, I'm sorry. I didn't mean dynamic. Non-indexed.
Pushed into the lambda.
Yes.
As opposed to being statically evaluated or being evaluated up higher.
Yes.
But then I had a question about how that implicated some of the. If you go back to the tree where you first started it.
I have a lot of slides.
Into the lambda was like an early stage of exposition.
Yeah.
Well, you don't need the code where you push it in the lambda, just the tree that you start the simplification from.
Yeah. I'm looking for it. I'll find it.
Oh, okay.
That's what I've done. I was looking at my slide sorter. So is it this?
Nope. It's the visible tree.
Oh, like the AST.
Yeah.
Oh, okay. Yeah.
So right here you said like, okay, C we're pushing into the lambda, but A and not B both were evaluating the earlier stage.
Okay. So
you push the C into the lambda and you simplify, you've removed the ability to put not B in that phase and also have to push not B into the lambda, don't you?
we don't have to evaluate not B because C is always true.
But C is only always true because you're going to reevaluate its truthiness in the lambda.
So in general, we don't put things in lambdas. That was, I think, early exposition. Like putting things in lambdas would not normally be the practice.
So we're talking about three different things. Okay. There's the index field and the non-index fields. So you're talking about C, and I'm saying I'm going to remove C because it's an index field.
Oh, I thought you removed C because it's a non-indexed field.
No, because it's an index field, right? So by the time we come to evaluate the rest of the predicate, it's guaranteed to be true.
Yeah, nope, I get it. I had it all backwards.
Okay. Okay, cool.
I didn't go forward. So you mentioned the fact that like compilers, optimizers, it's bread and butter for them to do these types of things, but they can't do it on our own types and with our own DSLs. And so I wonder if there's any way to hack the system. And like, for example, C++ concepts do have this like sort of a notion of trying to normalize the subsumption rules, take Boolean expressions, try to normalize them, and then try to find the best match, etc., etc. Was there any attempt to try and force that into the thing?
If it were possible, I don't know if it was, but if it were, I would still prefer Ben's code every time. Yeah. Okay, thank you, everyone.